Imagine unlimited clean energy, just from water and the power of the sun. That's what nuclear fusion promises. No carbon, no fuel shortages. In 2026, we're seeing real breakthroughs, but are we actually getting closer? Let's explore the science and find out.
Fusion is what powers the sun, smashing light atoms together to release huge energy.
On Earth, we fuse hydrogen into helium, releasing massive energy with almost no long-lived radioactive waste. The fuels are deuterium from seawater and tritium from lithium, enough in the oceans for millions of years of energy. The challenge: create sun-like heat over 100 million degrees and keep the plasma stable long enough to get more energy out than we put in. So how do we actually create these conditions on Earth? Let's look at the main reactor designs. Most fusion projects use magnetic confinement. The most common design is the tokamak, a donut-shaped reactor. Powerful magnets squeeze the plasma into a tight ring, heating it to over 100 million degrees Celsius to start fusion. Big projects like ITER in France and private ones like Spark use tokamaks to push toward ignition, more energy out than in. Stellarators use twisted magnets instead of a current in the plasma, making them more stable but harder to build. Stellarators offer better stability, no need for plasma current, but they are much more complex to construct. The big goal is ignition, producing more energy than the reactor consumes. We're getting closer every year. We're seeing real progress in 2025 and 2026. High-temperature superconductors make stronger, smaller magnets, enabling compact reactors like Spark. Private companies like Commonwealth Fusion aim for reactors 10 times smaller than ITER, but still powerful enough for high Q. Plasma durations are increasing, from seconds to minutes, a huge step towards steady-state fusion. Private funding has exploded, over $6 billion invested globally by 2026. The pace is accelerating fast. But big challenges remain. So why isn't fusion here yet? 3 major challenges remain. First, plasma instability. It's like holding wobbly jelly with magnets. Disruptions can damage reactors. Second, extreme heat. Reactor walls must withstand millions of degrees. New materials like tungsten help, but we need better solutions. Third, tritium fuel is rare. We must breed it inside the reactor from lithium. Scaling that is still very tricky. But progress is fast. Private companies build smaller, cheaper reactors. Many experts say commercial fusion could arrive in the 2030s or 2040s. Why does this matter? Fusion could give us unlimited clean energy, no carbon, no long-term waste, fuel from seawater. We're closer than ever, but not there yet. With continued effort, fusion could power the world in our lifetime. Let's wrap this up. Fusion could give us unlimited clean energy, no carbon emissions, no long-term waste, fuel from seawater. In 2026, we're closer than ever. Commercial fusion could arrive in the 2030s or 2040s with continued effort. The future is bright if we innovate responsibly, balancing science with safety and ethics. If this got you excited about fusion's potential, smash that like button, subscribe, and hit the bell for more science breakdowns. Drop a comment. When do you think fusion will power the world? I read everyone. Let's discuss. Thanks so much for watching. Stay curious about science. It shapes our future. See you next time, and thank you again. Stay curious.